Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at field extensions. So that's when you take a field F and you adjoin to it some elements that are not part of the field. So to understand a bit more about this, we need to know the degree of a polynomial. And that's just the highest power of x, because we learned previously a polynomial is just a map, and its rule is of this form, where the input is x, and the equation only has natural number powers of x. So something like x power 4 minus 2x squared plus 1 is a polynomial. It's a polynomial of degree 4 because the highest power of x is 4. So we need to know that because we need to know the degree of the minimal polynomial of k. Minimal polynomial of an element k is the polynomial of lowest degree with coefficients in the field such that k is a root. And we need to know that so that we know the degree of the field extension, because the degree of the field extension is just the degree of the minimal polynomial. So that probably doesn't make a lot of sense. So let's just look at an example. So an example of a field extension is q root 7. So q is a set of rational numbers, and root 7 is clearly not an element in q, it's irrational. So we can get another field by adjoining this. But to understand what the field looks like, we need to know about the minimal polynomial. So the minimal polynomial of the square root of 7, we want to find a polynomial with just rational or integer coefficients that has root 7 as a root. Now you can't find a degree 1 polynomial because x minus root 7 doesn't have rational coefficients, but x squared minus 7 clearly does. This is a polynomial. It has rational coefficients 1 and negative 7. And root 7 is clearly a root, because square root of 7 squared is 7. 7 minus 7 is 0. So the degree of this field extension is 2. And that's going to help us understand what this field will look like. So what happens is you basically go up to the powers that are 1 less than this. So what I mean by this, so q root 7, it will contain all the rational numbers. So I'll just let a be a rational number, plus a rational number times root 7. So q root 7 is all of the elements of the form a plus b root 7. So here we have the requirement that a and b must themselves be rational. So it turns out this will be a field, so all the usual rules apply. So let's look at something like q adjoined to the cube root of 7. So it turns out cube root of 7 can't be written as the root of a degree 1 or degree 2 polynomial with rational coefficients. So its minimal polynomial is x cubed minus 7. So just in case you were wondering, if you want to know that you have the minimal polynomial, you actually just check that it's irreducible. So we would just check that this can't be written as the product of two polynomials, again with only rational coefficients. So the degree of this field extension is 3. Now what I was talking about going up to powers that are 1 less than the degree, see this is degree 3, so its field is going to look slightly different to this. It's still going to include all the elements a plus b times the cube root of 7. But this alone wouldn't give us a field, because fields need to be closed under multiplication. So the cube root of 7 is an element of this field, and that means the cube root of 7 times the cube root of 7 must also be part of this field. So we need to include all elements of the form c times the cube root of 7 squared. So once again, a, b, and c must be rational numbers. And that's why finding the minimal polynomial is important. Because we knew it went degree 3, we have to go to this adjoined element to the power of 1 and to the power of 2. All right, let's look at some more field extensions. So if we have something like q of 1 plus cube root of 3 plus cube root of 4, If we just let x equal this number that we've adjoined, so we've only adjoined one number here, it turns out that this is a root of this polynomial. So this, again, is a field extension of degree 3. So this field will include all elements of the form a plus b. Now I'm just going to call it bx. What I mean is b times 1 plus cube root of 2 plus cube root of 4 plus c times x squared. We know to go up to x squared because the field extension is of degree 3, and once again, a, b, and c must be elements of the original field. So it turns out that these two fields are exactly the same. How do you say that two fields are exactly the same? Well, every element in this field is an element of this field, and conversely, every element of this field is an element of this field. So how do we adjoin something like this? Here we're adjoining two numbers. So because I'm adjoining the cubed root of 2, and I know that its minimal polynomial is just going to be x cubed minus 2, it is a degree 3 field extension. So if I want to adjoin the cube root of 2, I'm going to include all elements of the form a plus b times the cube root of 2 plus c times the cube root of 2 squared. Again, a, b, and c are rational numbers. But it turns out, of course, the cube root of 2 squared is exactly the same as the cubed root of 4. So the cube root of 4 is actually an element in this field. Because this field is all elements of this form, it will include any rational times this, any rational times this. Now, when you're including these, you also have to include their product. So because a field is closed under multiplication, I would have to also include any element of the form d cube root of 2 times e cube root of 4. So again, d and e are rational numbers, but the point is cube root of 2 times the cube root of 4 is the cube root of 8, which is just 2. Any element of this form will be a rational number, so it's included by a here. So I don't need to write this out as part of the elements of this field extension because it's going to be rational anyway. So note that if I just wanted to adjoin q to the cube root of 4, I would get this. So all of the elements of this field could be written in this form. Note that cube root of 16 is just cube root of 4 squared. So these probably look like they're different fields. But the cube root of 16 is the cube root of 2 times the cube root of 8. And the cube root of 8 is rational. It is 2. So I don't need to write this cube root of 16. This will just be a rational, any number of this form will just be a rational number multiplied by the cube root of 2. So I can rewrite this like this. So now you can see these are exactly the same field. Cube root of 2 squared is the cube root of 4. So as I said before, every element in this field is an element of this one, and conversely, every element of this field is an element of this one. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.